Practice problem number 3. A roller coaster comes to a halt at the top of a 75-meter hill. If the car starts to roll down the hill, what will its speed be when it reaches the top of the next hill, which is 40.0 meters high? These are fun. Okay, mostly because I love roller coasters. All right, we know that this hill here where we're starting is 75 meters high. 75 meters. And we know that the hill where we're going to end is 40 meters high. Now I want to introduce something new here, and that's a strategy. Set up a strategy before you ever start doing calculations. Ask yourself, what would be a good way for me to solve this, right? So this strategy, since what we're trying to find is the speed at the end, right? We're trying to find the speed at the end. That's our velocity. Well, it's not really velocity, it's just speed at the end. We know that kinetic energy is going to help us do that, right? So if I could know the kinetic energy here, I could find the speed. Okay, I can't do that just yet, but guess what I can do? I can use conservation of energy to solve this problem. So I'm going to begin, and you're going to see this a lot. Find the total energy, and I want you to take a look at the words I use in a convenient place. Once I know the total energy, think about this. When I'm here, I know that I've got potential energy plus kinetic energy. Well, guess what? Potential energy is totally easy to figure out, right? It's just mgh. So if I could take the total energy and subtract out the potential energy, I'd be left with kinetic energy. And if I have kinetic energy, I can find velocity. So here's my strategy. Find the total energy, then I'm going to compute the potential energy at the second point. We'll call that point B. You can see that there, point B. Once I know the potential energy, I'm going to subtract that potential energy from the total energy to get kinetic energy. And once I have the kinetic energy, I can solve for V. Okay, so I'm going to clean this up just a little bit here. Now that we've talked through the strategy, you know what's going on. All right, so let's follow that strategy. The first thing I'm going to do is find total energy in a convenient place. Well, equation 8.4 tells me that the total energy is equal to potential plus kinetic. All right, so I'm going to start out at position A. So here's position A. And when you look at that, this thing is not moving. So guess what? There's no kinetic energy. It's all potential. So the total energy is actually equal to just the potential energy. That's because the kinetic energy is 0. It's kinetic energy 0 because we're not moving. You're going to do this a lot. Get used to it. All right, so the total energy, which is equal to the potential energy, is equal to mgh. That's equation 8.4. Easy enough, right? M times g, 9.8 meters per second squared, times the height, 75 meters. A note about units, right? Meters per second squared, meters. That makes us happy. We're working in the units that we like. That's all good. Now you might be bumming because we don't know what m is, but don't sweat that. You're going to find one of the cool things about physics is things disappear. All right, let's look at part 2 here. Compute the potential energy at the 40-meter hill. Okay, well that's pretty easy. It's just mgh, right? Well, I don't know the mass, but I do know g and I do know h. So when I go to point B, that's the 40-meter hill, right? I'm just going to call that B just to make life easy. Potential energy is equal to this. Easy, right? I know what g is. I know what h is. I can fill those out. Those are really easy. Okay. M, still don't know what it is, but that's okay, because watch what's going to happen. We go to the third step in our strategy. The kinetic energy is total energy minus potential energy. Okay, so here's my equation. Donkey Kong eats stray cats. Gray cats, that's funny. Okay, so let's solve this thing. I'm going to get rid of that E that I just wrote because it makes it look like it's part of the equation. All right, kinetic energy is 1/2 mv squared. Right? Total energy minus potential energy. Well, total energy I already figured out. It's right here, right? I figured it out. It's 9.8 times 75. So here is the expression for total energy. Now, again, I ran out of space, so I'm going to do it this way. Minus, right? That was minus. We're going to subtract the potential energy. And here is the potential energy that I'm going to subtract. All right, so now I move over here where I've got enough room, okay? I've got enough room to actually do this problem. You know, I meant to go back and erase this, all of this. Okay, so you can ignore that. All this does is the same thing that we just did a minute ago. Now let me pan this up a little bit so you can see it. This problem looks a lot worse than it is, so don't let that freak you out. Okay, we just did this. Kinetic energy equals total energy minus potential energy. Easy. So at B, now remember we had this thing, right? Had the roller coaster up here at A, where everything was potential. We're at B now. Okay, at B, we're going to say that 1/2 mv squared, that's kinetic energy, right, is equal to total energy, boom, right, total energy, which we figured out up above, minus potential energy. And that potential energy is right here. Pretty easy, right? Pretty easy. When you solve this, you're going to see, I'm going to use a different color here, you're going to see that we can factor an m out. And guess what? When you factor that out, you get an m out front. You can also factor out a 9.8 meters per second squared. That's pretty cool, right? 9.8 meters per second squared. We factor those out, and we multiply it by whatever is left. Now this is just algebra we're doing here. 75 meters minus 40 meters. Pretty easy. Well, guess what's going to happen to those m's? There's one on the left, there's one on the right. Bada bang, bada boom. We never had to know what the mass was anyway. Pretty cool. The rest of this, just punching numbers in a calculator, mostly. 1/2 v squared, there's no more m, equals, we've got our 9.8 meters per second squared. 75 minus 40 is 35 meters. That's why we have this. So v squared, I'm going to multiply both sides by 2 to get rid of that fraction, right? Do that. And I end up with my 2 here. I'm just teaching you how to do algebra, probably wasting your time. All right, so v squared equals all of that. V equals the square root of all of that. And then v equals 2.62 times 10 to the minus 1 meters per second. Back to sig figs. This is the one that usually limits us, and it does this time too, so we've got 2 sig figs. The speed is 2.6 times 10 to the first meters per second. Now let's think about what we did, okay? Because what's more important is that you be able to do this in the future. This has to do with conservation of energy, right? Our total energy here was entirely potential. Interesting, if you wanted to look right here, okay, put the little guy here, there our total energy would be kinetic energy, right? That's assuming that we never go any lower than that. All right, you get back up here, guess what? Our total energy is a combination. It's going to be potential energy, because the thing is moving, right? I'm sorry, potential energy, because it has a height, sorry, because it has a height, because this hill goes on, right? And it has kinetic energy, that's okay, doesn't look like it, kinetic energy, because it's moving. All right, that was practice problem number 3. Hope that was helpful.